So let's take a look at the ratio test. Now the formula for the ratio test, let's say I have the series from n equals 1 to infinity of a sub n. If I take the limit as n approaches infinity of a sub n plus 1 over a sub n, and let's say that equals some value L. If L is less than 1, then the series from 1 to infinity of a sub n is absolutely convergent, and therefore it is convergent. If L is greater than 1, then the series is divergent, and if L is exactly equal to 1, then it is inconclusive. And we cannot make any conclusion about whether the series converges or diverges using the ratio test, so we have to switch to another test. So for number 1, we have the series from 1 to infinity of n over 2 to the n power. Now remember, for the ratio test, we have to take the limit as n approaches infinity of a sub n plus 1 over a sub n. Now a sub n plus 1, what that basically means is you just take n and replace it with n plus 1. So we're going to take this sequence and replace all n values with n plus 1. So a sub n plus 1 is going to be equal, if we plug in n plus 1 into that sequence, we'll get n plus 1 over 2 to the n plus 1 power. So remember, once again, we took all the n values and replaced them with n plus 1. And that is what a sub n plus 1 is equal to. Now a sub n is obviously just a regular sequence. So we're going to take a sub n plus 1 over a sub n. So we'll do n plus 1 over 2 to the n plus 1 divided by a sub n, which is equal to n over 2 to the n. So to simplify this, whenever we're dividing by a fraction, we're going to multiply by its reciprocal. So 2 to the n over n. And so when I simplify, we'll have the limit as n approaches infinity of 2 to the n times n plus 1 over 2 to the n plus 1 times n. So now to simplify, what I can actually do with 2 to the n plus 1 is separate it out using properties of exponents. So I can break this up into 2 to the n times 2 to the first, or just 2. Because when we multiply by terms of the same base, the exponents will add. So I'm going to rewrite this limit to 2 to the n over n plus 1 over 2 to the n plus 1, which is equal to 2 to the n times 2, and obviously times n. Notice the 2 to the n's will cancel, and we are left with the limit as n approaches infinity of n plus 1 over 2n. Now remember, when it comes to n behavior, we're just looking at the highest degree of the numerator and denominator. The highest degree of the numerator is n, and the highest degree of the denominator is 2n. And when the degrees are the same, they're both n to the first, then we just look at the ratio of the coefficients. So it's going to be 1 over 2. So the limit as n approaches infinity of n plus 1 over 2n is 1/2. Once again, 1/2 is less than 1. So that means this series of n over 2 to the n from 1 to infinity is going to be absolutely convergent by the ratio test. So looking at number 2, we have the series from n equals 1 to infinity of n times the negative 3 to the n over 4 to the n minus 1. Now you can use the alternating series test on this, since negative 3 to the n is an alternator, but it is also a good idea to use the ratio test. Now once again, in the ratio test, we're going to take the limit as n approaches infinity of a sub n plus 1 over a sub n. So once again, a sub n plus 1, we take every single variable, that's n, and we're going to replace it with n plus 1. So that is going to be equal to n plus 1 times negative 3 to the n plus 1 over 4 to the n plus 1 minus 1. Now obviously the plus 1 and minus 1 cancel, so we can simplify this to n plus 1 times negative 3 to the n plus 1 over 4 to the n power. So obviously that is our a sub n plus 1, and we're going to take that and we're going to divide it by a sub n, which is just our given sequence. So we're going to divide that by n times negative 3 to the n over 4 to the n minus 1 power. Obviously when we divide by a fraction, we're going to multiply by its reciprocal. So we're going to multiply it by 4 to the n minus 1 over n times negative 3 to the n power. Now similar to the previous problem, we can actually break up a couple of these exponents. Since 1 is being added to n here, this is just going to be a multiplication. So negative 3 to the n plus 1, we can break that up into negative 3 to the n times negative 3 to the first. Because once again, when we multiply the same base, we're going to add the powers. And then 4 to the n minus 1, since there's a subtraction sign here, these are actually going to be divided. So we get 4 to the n over 4 to the first, or just 4. When we divide the same base, we're going to subtract the powers. So now if I were to replace these with what I've broken down here, I'm going to rewrite it as n plus 1 times a negative 3 to the n plus 1 power, which is broken down into negative 3 to the n times negative 3 to the first, or just negative 3, times 4 to the n minus 1, and that is broken down into 4 to the n over 4, all over what we have in the denominator, which is just 4 to the n times n times negative 3 to the n. So now this is all a matter of elimination, so notice the negative 3 to the n's will cancel, the 4 to the n's will cancel, and so we're left with the limit as n approaches infinity of n plus 1 times negative 3 over n. If I distribute the negative 3, we'll get negative 3n. I'll put the limit notation first. So the limit as n approaches infinity of negative 3n minus 3 over n. And once again, when looking at n behavior, we're just looking at the most significant terms, or the highest degree of the numerator, which is negative 3n, and the denominator, which is n. The degrees are the same, so we're just going to look at the ratio of the coefficients of the highest degrees, which is just going to be negative 3 over 1, which is negative 3. Obviously negative 3 is less than 1, which means the series is absolutely convergent by the ratio test.